Hello and welcome to BiochemSerye, or the Biochemistry Lesson Series. This series is entitled The Basics of Chemistry. It is important that we review some basic concepts of chemistry before we dive straight onto studying the much more complicated world of biochemistry. This series is composed of 6 lessons. Please feel free to subscribe to be updated of the latest lesson installments for this series. This is the 4th and last episode of the Basics of Chemistry Lessons series and includes Lesson 6. Please click on the card above if you want to see all the videos in the Basics of Chemistry playlist. Lesson 6 discusses the concept of chemical reactions and examples of such. Please remember this is just a primer to the different chemical reactions and thus are simply and quickly presented. The preceding lessons are listed in the playlist. Please subscribe and click on the notification bell to be notified of the other lesson series uploads. To start, let us define what chemical reactions are. Simply stated, chemical reactions are processes in which electrons or groups of atoms are taken up into molecules, exchanged between molecules, or shifted within molecules. Others define a chemical reaction as a process that leads to the chemical transformation of one set of chemical substances to another. Classically, chemical reactions encompass changes that only involve the positions of electrons in the forming and breaking of chemical bonds between atoms, with no change to the nuclei. That is, no change to the elements present, and can often be described by a chemical equation. We will now illustrate the most important types of reactions in organic chemistry and consequently in biochemistry, using simple examples. The first of the chemical reactions we will be discussing is the redox reactions. Redox reactions are oxidation-reduction chemical reactions in which the reactants undergo a change in their oxidation states. The term redox is a short form of reduction-oxidation. All the redox reactions can be broken down into 2 different processes: a reduction process and an oxidation process. The oxidation and reduction reactions always occur simultaneously in the redox reaction. The substance getting reduced in a chemical reaction is known as the oxidizing agent, while a substance that is getting oxidized is known as the reducing agent. In redox reactions, electrons are transferred from one molecule, the reducing agent, to another, or the oxidizing agent. 1 or 2 protons are often also transferred in the process. But the decisive criterion for the presence of a redox reaction is the electron transfer. The reducing agent is oxidized during the reaction, and the oxidizing agent is reduced. In this illustration and the succeeding ones, electron shifts are indicated by red arrows. This illustration shows the oxidation of an alcohol into an aldehyde, shown as reaction 1. And the reduction of the aldehyde to alcohol, or reaction 2. In the process, 1 hydride ion, or what is known as 2 electrons and 1 proton, is transferred, which moves to the oxidizing agent in reaction 1. The redundant proton is bound by the catalytic effect of a base B. In the reduction of the aldehyde, shown as reaction 2 here, IH serves as the reducing agent and the acid HB is involved as the catalyst. In contrast to redox reactions, only proton transfer takes place in acid-base reactions. In general, acids are defined as substances that can donate hydrogen ions, or simply protons, while bases are compounds that accept protons. When an acid dissociates, seen here in reaction 1, water serves as a proton acceptor. That is what acts as the base. Conversely, water has the function of an acid in the protonation of a carboxylate anion, as seen here in reaction 2. To continue our discussion on acid-base reactions, let's look at this illustration. Acid-base reactions always involve pairs of acids and the associated conjugated bases. The stronger the acid or base, the weaker the conjugate base or acid, respectively. For example, the very strongly acidic hydrogen chloride, seen here as number 1, belongs to the very weakly basic chloride ion. Conversely, the weakly acidic ammonium ion, number 3, is conjugated with the moderately strong base ammonia. Moving on, a reaction in which atoms or molecules are taken up by a multiple bond is described as addition. The converse of addition, that is the removal of groups with the formation of a double bond, is termed elimination. When water is added to an alkene, shown as 1A, a proton is first transferred to the alkene. The unstable carbonium cation that occurs as an intermediate initially takes up water before the separation of a proton produces alcohol, seen here as 1B. The elimination of water from the alcohol, 2B, or dehydration, is also catalyzed by an acid and passes via the same intermediate as the addition reaction. The next reaction we are going to discuss is that of substitution. A reaction in which one functional group is replaced by another is termed substitution, depending on the process involved. A distinction is made between nucleophilic and electrophilic substitution reactions. Nucleophilic substitutions start with the addition of one molecule to another, followed by elimination of the so-called leaving group. The hydrolysis of an ester to alcohol and acid, seen here as reaction 1, and the esterification of a carboxylic acid with an alcohol, reaction 2, are shown here as an example of the nucleophilic substitution mechanism. Both reactions are made easier by the marked polarity of the C-double bond O, in the form of ester hydrolysis shown here. A proton is removed from a water molecule by the catalytic effect of the base B. The resulting strongly nucleophilic OH ion attacks the positively charged carbonyl carbon of the ester, seen here as reaction 1A, and an unstable sp3 hybridized transition state is produced. From this, either water is eliminated, shown here as reaction 2B, and the ester reforms, or the alcohol ROH is eliminated, represented here as reaction 1B, and the free acid results. In esterification, reaction 2, the same steps take place in reverse. And lastly, let us look into the rearrangement reactions exemplified by isomerization reactions. In rearrangements, groups are shifted within one and the same molecule. Examples of this in biochemistry include the isomerization of sugar phosphates and of methylmalonyl coenzyme HA to succinyl coenzyme HA as seen here. This concludes the sixth and final lesson in the Basics of Chemistry lecture series entitled The Concept of Chemical Reactions. Thank you very much. Thank you for watching this episode in this playlist. Check out the other videos in this playlist, and please do subscribe to our channel and click the bell to be notified of new video episodes that will be regularly uploaded.